right, so now we get to kind of come full circle to using stoichiometry with an ideal gas law. So what's going to happen is you're going to have an equation that is going to have a mixture of solids and liquids and gases. And any of the gases, you're going to be able to get, for example, moles from something other than just mass. When we're talking about moles, we can now find moles from mass. So for example, if it's a solid, you'll have grams of species A, and then you will multiply it by the molar mass or divide by the molar mass to be able to figure out how many moles there is. You also may be given a solution where you know the molarity and you know the volume. So you can do moles equals molarity times volume. But now we're going to add in that you can find moles using the ideal gas law by doing PV divided by RT. So all of these were to find the moles of a species. Then once you have a mole of a species, you can go mole to mole, and then from that species they could then ask you, how many grams do you have of that species? How many liters do you have of this species? Or what's the molarity of that species? And then maybe they want to know pressure or volume or temperature of another gas in the equation. So let's look at some examples to see what I mean. So this question says, how many liters of carbon dioxide will be obtained? So when we're talking about how many liters, I know I'm talking about volume. So for carbon dioxide, they want to know how many liters, or what's the volume of carbon dioxide obtained or produced at a pressure of 745 millimeters of mercury. Now hopefully you're at the habit now where as soon as you see millimeters of mercury, you just change it. So I'm going to go that 1 atmosphere is 760 millimeters of mercury, right? And then that'll give me some pressure. And the temperature being 27 degrees. And again, I'm going to go straight to changing that to kelvins. And let's just get these two answers. So 745 divided by 760. I have to store this. So 0. And again, this is exact, so we don't use it in our sig fig. So 0.980 dot dot dot. And I'm going to store this as A. And then store A. And then I'm going to take this other guy, 27 plus 273.15. And you can store that one as well. It's not a huge number to type in, so you don't have to. But 300.15. And again, we have temperature to the ones. So we're going to say that this is 300 kelvins, but we're going to record it as 3 sig figs, just like we did up here. And what they want to know is how many liters, the volume. So we need to know moles. We need to have 3 pieces of information to find the 4th. Well, the other information they gave me is that we're starting with 15 grams of the calcium carbonate. So from calcium carbonate, grams, we're going to go to moles, and then we're going to use a mole-to-mole ratio to find out how many moles of carbon dioxide are produced. So let's start with the 15 grams of calcium carbonate. We know that 1 mole of calcium carbonate weighs how much? Well, we've got calcium carbonate. So we have 1 calcium. Each calcium, where did my formula sheet go? Oh, one sec. Okay, so 1 calcium is 40.08 grams per mole. And then 1 carbon is 12.01 grams per mole. And then 3 oxygens that are each 16 grams for a total molar mass of 40.08 plus 12.01 plus 3 times 16 gives me 100.09 grams per mole. So 1 mole of calcium carbonate weighs 100.09 grams. So now to convert that, I'm going to type in 15 divided by that answer, which is going to give me 0. Let's keep track of sig figs, so I'm at 3. So 0.14 dot dot dot, I'm not rounding because it's not a final answer, moles of calcium carbonate. Now I could have at the same time, if you can look ahead and be like, oh, but what we really wanted moles of carbon dioxide, we are then going to use our mole-to-mole ratio, so say that 1 mole of calcium carbonate produces 1 mole of carbon dioxide. So therefore we have 0.14, oh, I didn't write enough down, 149 3 sig figs moles of carbon dioxide. So then for here, I now have 3 pieces of information to find the fourth. I'm going to use PV equals nRT to solve for V. So V is going to equal nRT divided by P, and I'm going to put in all my information. So 0.149 times 0.08206 times 300.15, keeping track of sig figs, that's only 3, divided by the pressure, which is that 0.980 ... or my A value. So now, plugging this all into my calculator, I've got this answer in my calculator. I'm going to times by 0.08206, times by 300.15, and divided by, for me, I've got recall A, and I end up to 3 sig figs, getting 3.77 liters. I almost wrote atmospheres. So we're combining our love of stoichiometry with our ideal gas laws in our last unit. Okay, one more question. If you feel like you can do this one, give it a go. Otherwise, if you're feeling kind of lost, you can just stay with me. So this one says, how many liters of oxygen at standard temperature and pressure will be required for the combustion of 10 grams of ethane? So my mass of ethane is 10.0 grams. So I know I could use this to find moles of ethane, to find moles of oxygen. It again wants me to find volume of oxygen at standard temperature and pressure. So the temperature is going to be 273.15, and my pressure is going to be that 1 atmosphere. What I'm missing is moles, but it's not going to be a question mark because I'm going to know it shortly. So we're going to start again with that 10 grams of C2H6, and we're going to find how many moles that is. So we know that 1 mole of C2H6 weighs what? Well, C2H6 is made up of 2 carbons, which are each 12.01, and 6 hydrogens, which are each 1.008, which will give me 30.068 grams per mole. So 1 mole weighs 30.068 grams. And then we plug it in. 10 divided by that answer gives me, to 3 sig figs, 0.332 ... moles of C2H6. Now again, it's funny, I usually remember to keep going because I know I'm going to moles of something else, but for some reason in this video I'm not. So now I'm going to take that and I'm going to go to moles of oxygen. So I know that 2 moles of C2H6, or ethane, will combust with 7 moles of oxygen. So I'm going to take that answer, I'm going to times it by 7 and divide by 2. And again, you could have done that in one big long line. And I will end up with 1.16 ... moles of O2. So that's going to be my answer for up here. So then just like before, we're going to use the equation V is equal to nRT over P. And I know the moles is 1.16. The R is 0.8. Oh, I always want to do that. I always forget the 0. It feels like such a small number for a constant. 0.08206. The temperature is 273.15. I'm really hungry. Sorry about my stomach. Divided by that 1 atmosphere. And again, the 1 is not included in my sig figs, so I'm going to give 3 sig figs in my answer. So I'm going to hit times 0.08206 times 273.15 divided by 1, which to 3 sig figs gives me 26.1 liters. Awesome. Okay, go practice those because the next questions we're going to do are limiting reagent problems, which are just bigger.